The separation of linear alcohols is of industrial importance, and I consider today the separations of one alcohols using Chabazite zeolite that has a cage window structure. The cage size is approximately 8.5 angstrom, and each cage is separated from adjoining cages by windows that are approximately 3.8 angstrom in size. The unary isotherms for 3 linear alcohols are shown here. These unary isotherms were determined from configurational bias Monte Carlo simulations. The green squares are for ethanol. The blue triangles are the unary isotherms for the 1-propanol, and the inverted red triangles are the unary isotherm for 1-hexanol. As the chain length increases, so does the strength of the binding between the linear alcohols and the framework atoms. Indeed, if we plot the polarizability of the linear alcohols as a function of the molar mass, we see the polarizability varies roughly linearly with the molar mass of the 1 alcohols. Another point to note is the saturation capacities decrease with increasing chain lengths, because the cages of Chabazite can only locate 4 ethanol molecules, a maximum of 2 1-propanol molecules, or just a single 1-hexanol molecule. So, summarizing the results here, the binding strengths increase with the increasing chain length. However, the saturation capacities increase with decreasing chain lengths. Let's look at a set of experiments on the breakthroughs of mixtures of 1 alcohols using Chabazite as a adsorbent, and these breakthrough experiments were conducted in the liquid phase. I plot here the breakthrough experiments reported by Denaye and co-workers, published in Journal of Physical Chemistry C in 2011. We have a set of 2 breakthrough experiments with feed mixtures of ethanol and 1-propanol in proportion of 50-50 operating in the liquid phase, and the component to breakthrough first is the longer 1-alcohol molecule, in this case 1-propanol. Another set of breakthrough experiments with feed mixtures of ethanol and 1-hexanol are shown here on the right hand side, and we note here that the component to breakthrough is the alcohol with the longer chain lengths. So at first sight, these experimental breakthroughs appear to be paradoxical, because the binding strengths of the 1-hexanol and 1-propanol are larger than the binding strengths of ethanol, but the sequence of breakthroughs is not dictated by the binding strengths, but rather by considerations other than strength of binding. Indeed, as I have explained in my other YouTube presentation titled Exploiting Entropy Effects on Mixture Separations, the separations of mixtures of 1 alcohols in the liquid phase are strongly governed by entropy effects that favor the guest molecule with the higher saturation capacity because these molecules pack more efficiently within the cages of Shabbosite zeolite. So the takeaway message from this short presentation is that for operations or separations that operate in the liquid phase, the mixture separations are governed by considerations other than binding strength. Indeed, the entropy effects are dominant in the examples of mixtures of linear alcohols.